So, how's everyone? Has everyone read the paper?
I read the paper, but I definitely skipped most of section 3.
Yeah, I would
I
agree.
missed,
Section 3 is the theory stuff, right?
yeah, most of an operator is a contraction.
Yeah, that part definitely can be very frustrated, and I would agree. I was skipping that. I think they're trying to give a justification of the Bellman equation using the distributional Bellman equation. But for the most part, yeah, I just kind of skipped it. Any other thoughts with the paper, just on a very high level?
Difficult.
Difficult? Yeah. I agree. It's definitely not the paper that is the easiest to read. This is my second time trying to read it through, and I think it makes more sense. But the first time, I absolutely did not get what it's trying to say. Well, I understand it on a bigger picture, but not in detail. I think this time I understand a little more on the details. Any other thoughts?
So yeah, I actually found some few resources online, like presentation, like video talk, given by the authors. So it was much more, user friendly.
Oh, okay. Do you mind sharing that video in the monthly dev channel?
Yeah, sure.
Yeah, sounds good. I also found something that has helped me to understand it. There's a couple of pictures by a blog post, but we'll get into that. All right, I think let's get started with the distributional RL presentation. So yeah, the name of the paper is a distributional perspective on reinforcement learning. And as always, I posted the annotated PDFs online, which is this second Google Drive link. By the way, I'm going to share this link to the Slack channel. In case you want to check it out. All right. And since Lucas says this is useful, I think I'm going to include this link as well. And I'm probably going to check it out later because I think looking at some videos will probably help me to understand it a little more. And this is the link to the original paper. This is the annotated PDF, which if you look at, looks something like this. And I'm probably gonna include the explanation for different colors in the slides as well. All right, and something else that has really helped me is this blog post that has some very good pictures, in my opinion, explaining what the correction of the distributional RL, which is kind of a technical details, what they mean. And so these are some of the useful informations. I'll just sort of add the link Rosalind put in the Slack channel as well. And now let's sort of have a quick rundown of the paper. I think the core idea of the paper is actually not that complicated, but the math part in section 3 is definitely very intimidating. But overall, what the paper is trying to talk about is instead of maximizing the expectation of rewards, maybe you should trying to maximize the value distribution. So when you calculate the Q value by using the standard value approach, the Q values is equal to the expectation of rewards plus gamma times the expectation of the Q value of the next states and the next actions. However, a distributional perspective would say, instead of asking for the Q value, I am going to get a distribution based on the current state and the current action. And by doing so, I remove the expectation on the random variable rewards and remove the expectation on the, well, replace the expectation of the Q value of the next state and next action with the distribution of the next state and the next action. So that's kind of the idea of the paper. And as far as how you would enable the agents to learn on a very high level, is the bottom one, where the top one is how you would update the traditional DQN, which is to minimize the distance between expectations. You're minimizing the TD, temporal difference errors, and the temporal difference errors is this reward plus a gamma times the actions that results the best Q value in the next states. So this can be think of as the sort of the new value, and the QSA could be think of as the old value. So the old value and the new value should be theoretically equivalent. That's why by minimizing the distance between them, you can let the agent to learn. And with the distributional perspective, which this algorithm is abbreviated as C51, or I think a lot of people call it distributional DQN. So in the case of this algorithm, you're trying to minimize the distance between distributions, right? So here you're trying to say, I forgot what soup means.
Premium, I guess, a different type of maximization.
Maximization. Well, it doesn't make sense if it's maximization, right? You're maximizing the distance, but really you should be minimizing the distance. I think it means a premium.
Yeah. Minimum is minimum, premium is maximum.
Right, okay. So premium distance of that. Wait, so why would you maximize the distance? Oh, right, because it is minimized. Sorry. Let's take a look at the definition of them real quick.
In the paper, they say the premium, the maximum form of the Wasserstein metric. And they have symmetric over value distributions, which we call skipped. And then.
Wait, so say that again.
It's in the paper, they say the main tool for the analysis is the Wasserstein metric, which is the kind of infimum over two distributions. And then you're basically trying to maximize that minimally.
Okay, so sort of maximizing the minimum, something like that. But never mind. I'll get into the details of this. But for now, the least upper bound. Right. Oh, I see. It's the least upper bound. It's a minimum of their differences, something like that. But you're still trying to minimize the distance. Yeah, I can get into the detail of this, but I think the intuition is to just understand that the C51 is trying to minimize the distance between distributions. Right? I think the soup is, now that I think about it, it means maybe if you're it's like comparing the, yeah, never mind. So we're going to kind of skip section 3 because it's very mathy, and I don't think it offers a lot of intuition as what they're trying to do, but instead look at section 4 and try to understand what the algorithm is actually doing. So if you look at the description of what they're trying to say, is that we modeled the value distribution using a discrete distribution parameterized by n in the natural number, and vmin and vmax in the real number, and whose support is the set of atoms. And the atoms is defined as Zi is equal to this V min plus essentially the distance between these atoms. And then from a visualization standpoint, it's basically a probability mass function, right? In a discrete case. And then Z1 might be this, and Z2 might be this, and you go all the way up to Zn. So in this case, n is equal to 25. So if we take n equal to 25, the x-axis will be these zi's, and then each zi is calculated with a probability, and the probability is calculated by using the neural network with respect to the current state and the current action. So you might get something like this. Where in some ZIs you have an extremely high probability, while in other ZIs you have very low probability. And this is essentially kind of the core of the paper, where they're saying, okay, now we have this Z, and we're trying to get whatever is on the right part, right? And the right-hand side can be calculated sort of using this complicated things. And hopefully in this presentation, we can further understand what this is actually saying. So the author kind of suggests that it can be visualized by the pictures on the right-hand side. So essentially, when you multiply the gamma, you sort of shrink the distribution to a smaller size, and then when you plus the reward, you get this. But notice how its position is different from the original distribution, which is this Z on the left-hand side. That's why they propose this operator to sort of adjust their position so that they match the ZI. So the blog post that I look at explains it in sort of this different way. And the paper calls it the transformation, where imagine if you start with a bunch of xi and pi's. The problem is, after you calculated the right-hand side of this equation, they become this sort of r plus gamma times xi, but now they're not in the standard positions like in this sort of PMF. The xi will be shifted maybe somewhere in the middle, and maybe you have another x2 after multiplying by gamma plus reward, maybe somewhere in the middle of this instead of being x2 or x3. So that's what this blog post is trying to say. This by itself might be some green dots between two different atoms, or the support of the distribution, as I call it. And the author of this paper essentially proposed a way for you to distribute these atoms to the standard positions, the ZIs that is designed initially. So the way you do that is by sort of reading through this paragraph, where say, if the green has atom W, you essentially distribute part of its weights towards the closest atom it can find, and then distribute sort of some part of its weights to other positions. It's also I see. Okay. Yeah, so that's and then it's possible for one of the positions, such as xi or zi, to receive contribution. So the authors sort of call this blue vertical line over here the contribution from a misaligned atom, and then what the algorithm does is to sum up all of the contributions from all of the atoms that could have contributed to it. And if you look at the algorithm, one thing that remains to answer is this part trying to do exactly this part? Well, we can do some sort of analysis. So if you look at it, it's saying the transformed Zi, which is sort of which is whatever is on the right-hand side, and they should match with the Zi on the left-hand side after the transformation. And then it's saying the transformed Zi sort of being cut off by the Vmax and Vmin, and then minus the Zi divided by the distance between them, blah, blah, blah. But I think maybe what will help us to understand what it's actually trying to say is to use an example. So imagine the transformed Zi is very far away from the actual Zi. So the Zj is very far away from the Zi. What would this whole thing calculate? Well, if you think about it, if they're very far away, the value on the top of this equation is going to be very large, and then we know the distance between each Zi is constant, so this value will be very large, and when you use 1 minus it, the value inside will likely be negative, and that's why it's clipped below by 0. Therefore, if a misaligned atom is very far away from Zi, it has no contribution towards this calculation. However, if they're very close together, then essentially this number here will be the number at the top of this fraction will be very small, and then overall 1 minus this will be could be something very large. Or, now that I think about it, the maximum it can be should be 1, right? So there's no reason to bind it above by 1, because this should be a positive fraction, and 1 minus a positive fraction should always be greater than 0. But in any case, this number will likely, whatever is inside, will likely to be equal to 1, therefore have a positive contribution. So in a nutshell, it's saying if the misaligned atom is sort of close to the Zi atom, then it'll have a positive contribution of its probability, and then we sum all of these probabilities up, provided that the misaligned atom is close to Zi. So I think that sort of matches the description by the blog post over here, where it's essentially saying if you're close to the atom, then you can contribute. Otherwise, if you're very far away, let's say the green atom is over here, it's not going to contribute because of the zero cutoff. So therefore, after you constructed these two probability distributions, the transformed tau z theta, and then you have the z theta given the original states, what you're going to do is to minimize the KL divergence from them. This sort of reduces to a multi-class classification, and then you can use the cross entropy to solve it. So I think that's basically the bulk of the algorithm, and then it has very good results on Tari. I think that's essentially the big part of the paper. And does anyone have any questions?
So the contraction bit, that's just from applying the discount factor?
So you mean from A to B?
From A to B, yeah. That's just applying discount factor, I guess.
Yeah. I think just multiplying by the gamma is just simply, squeeze it. Does my presentation make you feel more clear of the algorithm is trying to do?
Yeah, I am bit clear.
Okay. Well, what would be the thing that you would be still confused? So I claim that I don't understand this algorithm completely, but I think what I was trying to do here makes a lot of sense to me. But
Can I ask?
yeah.
So is the categorical algorithm, what it's trying to do is basically model the buckets that come from that discretized, all the bins that go into that histogram. Is that what the algorithm is trying to model?
Yes, I think so. Yeah, you're trying to model, a bunch of bins given a current state and action, and then you're trying to minimize the distance between this bin and then the transformed bin, which is sort of calculated by the gamma and then the reward of the next state of the current state, and then sort of shifted in the ways that described below.
Okay, and so they describe the number of atoms. That's basically the number of horizontal bars in your histogram.
Yeah. No. The number of atoms is really the x-axis. So it's not how high the bar is.
No, but how many bars there are.
Yes, how many bars there are. So if you said n equal to 25, which is to say we want to have 25 atoms, it's sort of a approximation of a distribution because you can have it's trying to model the distribution of the returns, right? Your return could range from anywhere from 0 to 20,000 or 50,000. It's not computationally feasible to sort of model them individually, so that's why they use this vmin vmax. And now that you mentioned it, there's going to be limitations, right? What if you don't know what's the maximum value and the minimum value, right?
Exactly, there are many assumptions, right? Here, and the fact that actually, when you think about it, probably it's very computationally intensive, right? Algorithm, the whole algorithm.
Yeah, that's something that we're going to find out, right? And how you set the number of atoms and how computationally expensive it's going to be. But yeah, I definitely think there are limitations.
And we will have like a head for each action, right? Which is also limitation.
Beg your pardon? Have a hat?
We will have head over the neural network, like output for each action. So in the situation we have like many actions, right? It's not feasible. It's not probably possible to even use this algorithm.
So I think the input of the neural. So I think the output neural network is always going to be the number of atoms. So your output should be constant.
No, I
the
think
number
it's
of
an
action times the number of atoms.
Exactly.
Because for each action, we have to model the probability of the distribution of the returns.
Okay, I see.
Sorry for interrupting.
No, it's fine. Okay, so that might be implementation details. So maybe for the continuous action space, then what I said can be done, where the Q values can take into the action and the states. But I guess in the discrete, they probably just want to enumerate of all of the actions. Then yeah, it could be very computationally expensive. Yeah, especially I guess if you don't know the returns, what's the maximum return or the minimum return, then I would imagine then the distributional RL, you have to somehow approximate it, and the approximation can be very bad. But yeah, to sort of going back to the point that we were trying to say originally, the n is the number of atoms, which is on the x-axis. How many atoms there? How many discrete sort of points there are in the x-axis, and the probability is the vertical lines, or the how high the bars are in the chart.
So that will be the PDF output of the model, distributed Q model. The number of atoms, it will be the number of it will be the probability distribution of the actions, or sorry, my question doesn't make sense.
No, it's fine. It's just the discussion. Could you repeat your question, please?
No, my thing is like in the normal Q learning. I mean, like in the normal Q learning, so the output will be the input to the model will be a state action pair, and the output will be a Q value for that. So in distributed model, I think this will be a Q value distribution sort of thing.
So I think in standard DQN, in the discrete settings, you're inputting the states, and then the output will be the Q values for each actions.
Okay.
Yeah, and I think for the distributional RL case, then you would input the states, and then it'll output the number of actions times the number of atoms. So for each action, you have a you have a probability distribution over returns.
Oh, okay.
And I think the selection strategy, as far as how you select the action, is to select the action that results in the best return. There's going to be some sort of measurement. Maybe the mean return is going to be higher. You select the action that corresponds to the best mean return, or I don't know, something like that.
Oh, okay.
I'm sure this part is explained in the paper. Rosalind, do you know how they sort of select the actions?
That's actually the part I'm currently trying to wrap my head around. Not much.
Yeah, so if you look at the categorical algorithm, it says argmax of the Q function. Yeah, it's like, what does that even mean?
So we compare with the targets, right?
Yeah, but the targets that are being generated, if you look at each action corresponds to a set of atoms. So in other words, if I execute action 1, I'm going to have 10 items of possible returns. So if I execute action 1, there's a 5% of probability of getting return 0, 10% probability of getting return 20, 20% probability getting return 40, blah, blah, blah. And it doesn't make a lot of sense to me to just say argmax, because you're given a distribution. Your Q value is not a value, it's a distribution. And then you're trying to select, in some sense, the action corresponds to the best distribution, but the definition of the best distribution does not... What does it mean to choose the best distribution? Does that make sense?
I think so they mentioned in a paragraph that the neural network would give an output probability for every value atom, and they are using those probabilities to calculate the Q values for each A star is more like the offline or greedy action.
Yeah, I'm sorry, your voice is cutting off a little bit. Would you mind telling me which part of the paper or what page it is?
It's the same page where the algorithm is.
The same page as what?
The algorithm.
The algorithm. Okay.
Yeah. The right column, the first paragraph. Yeah.
Okay. For our study, we use a decanted structure, but I'll put the atom probabilities instead of action values, and choose from preliminary. We call this result as in DKON. The selection we leave. Yeah, exactly. We leave as future work the many ways in which an action can select an actions on the bias of the full distribution. Oh, I see.
That just use epsilon greedy to select the action bias.
I see. Yeah. So yeah. Okay. So it's using some sort of greedy policy to select the expected actions. So the expected actions will just be the mean of the distribution. Something like that, right? Okay, I think that makes perfect sense. So,
isn't that basically the expectation in this case?
So yeah. So I think what it's trying to say is that if we take a look at the, so this is the distribution, right? And then action corresponds. So imagine you have 4 of these, right? If you have 4 of these, which distribution is going to be better? Is going to help you decide which actions to choose from. And I think it's just using epsilon greedy is saying, if I'm doing exploration, I'm just going to randomly choose an action, of course. However, if I'm not being greedy, then what I'm going to do is to calculate the expectation of this distribution, which is the probability of this occurring times the atom itself, right? And you're summing up all of, which is essentially the mean of the distribution. And then whichever distribution has the highest mean will be the distribution that you choose the actions from.
Oh, I see. Okay.
Yeah.
Thanks
a lot for pointing that out, Krishna. Beg your pardon?
So the only difference during learning is the different loss functions. Rather than having a squared loss for the Q value, now you have this distributional loss. But the actual selection and action is still epsilon greedy.
So they're right. So when you do the exploration, yeah, I think it's just regular epsilon greedy. There's no depth into that. However, if you're not doing the epsilon greedy exploration, when you actually select an action, that's when you have to select from multiple distributions, right? I don't know which, and that's when. So for each action, you have this, right? So it's like, imagine you have.
So Z is just the discounted future rewards, right? That's not how we select actions, it's just how we're estimating our credit.
So for each action, right, you have this. Action 0, action 1, action 2. Well, let's just take a look at 3. Action 1, action 2, action 3, right? So given the states, you have this. And how you would select an action is you find out which distribution has the better mean, has a better mean value. Does that make sense?
Yeah, I think so.
Okay. But yeah, so that's the action selection strategy, I suppose, and then you can do all of the updates and stuff like that. Any questions or comments?
I was going to say on page, I can't find page numbers, but theorem 1, right below it, it says that this kind of negative result, that the mean of that case does converge quickly to Q star, but the distribution need not be well behaved.
Okay, compared to Theorem 1 to Lemma 4 reviews a significant difference between distributional framework and the usual setting. While the mean of ZK converges quickly to Q star, its distribution need not to be well behaved. So yeah,
If
that's
you're getting a badly behaved distribution, how will that be helpful at all?
so I think what it's trying to say is that your distribution might not look as good as this. So in other words, the neural network might just learn to optimize the distribution, meaning that if I want this action to be selected, I don't care about its other distribution as long as its mean is large. So yeah, I think that might be one of the limitation with the paper.
I kind of have some concerns. So, they mentioned that this implementation trains at roughly 75% of DQN speed, but looking at the pseudocode, there is a lot of math happening for a single given step.
Exactly. Yeah.
Where is the pseudocode of this?
The algorithm.
Oh, right, of course. What am I thinking? Let me take a look at the pseudocode real quick.
So even the algorithm mentioned is just a part of the what do you call it?
The training part?
This, yeah.
Yeah,
but
yeah.
They're not inside the DQN method.
Yeah, exactly. I think so. It's not a complete pseudocode.
And so at the bottom right corner, when they mentioned 75% for 51 atoms, so for a single step, it's kind of computing 51 times something additional more steps, and I'm surprised it's doing it with 75% of DQN speed.
So n equal to 51 would mean you
51 value atoms.
Yeah, 51 times the number of actions. That's how many logits the neural network would generate.
Yeah.
Yeah. So yeah, it's definitely slower, but it's not an exponential algorithm because it's upper bounded. It grows linearly with the number of atoms you want to add.
And even in the analysis, for a given environment, they've compared between various number of atoms, but not with the existing standards or benchmarks.
Okay.
I mean, it's kind of hard to see how better it is doing with respect to, let's say, DQN or some other algorithms.
Could you elaborate on that? Sort of say it again. Why doesn't it show it's better than DQN?
So let's say if we are training a given environment using DQN, maybe it's learning in 500 million frames or 500 million steps. And we don't know how many steps this particular implementation is taking to guard.
Are you saying comparing to the wall time, like how much time, like actual time the algorithm spent, then DQN, if it had more time to train on, it could perform better?
Yeah, I mean, so basically in every paper we would see a comparison between algorithms to showcase how better their implementation is with current benchmarks.
Yeah, I would agree. However, I would say one thing to notice is in a way, given the same number of training time steps. So even though C51 is taking longer physical time to train on, but it has better sample efficiency because you're still giving the same number of samples. That's why they fix the axis to be the number of time steps instead of physical times.
So does it have sample efficiency? I mean, technically it might have, I mean, from the looks of the algorithm, but they didn't do any analysis to show that it has a better sample efficiency than
So Well, sample efficiency is a loose term, right? I think overall what it's trying to say is, given the same number of training frames, can you get better? Can you get better performance? So if you can, you have better sample efficiency.
So are we assuming that? So let's say here, so all the environments are trained for 200 million training frames.
Yes.
But we don't. So in the graphs, there is no plot of what the actual DQN performance is for 200 million frames, just to compare.
I think they do, right? The DQN is the dotted line. So,
Okay.
So for example, it's this and whatever is at the bottom.
My bad. Sorry.
No, it's fine. It's fine. Yeah, and one thing to notice is that, when you're talking about sample efficiencies, the value-based approach almost always have better sample efficiencies. If you look at our benchmark and compare something, for example, like A2C to something like DQN, what you will likely find is DQN performs a lot better usually. Surprisingly, in carpool, DQN doesn't perform that well. But let's say if we...
It's because of the replay buffer, right?
Yeah, it's because of the replay buffer. You can reuse experience to train. I don't think I have a really good example. Maybe this is the only example.
But actually, it's kind of like similar approach to all these other like PPO approaches, where we actually taking where we using this computation to do more extensive like search over this possibility, like explore more, right?
I wouldn't call it explore more, but you're training more.
Yeah, exactly. You're training more. So basically, it's not a silver bullet, right? It's not something that you can scale, right?
Right.
So that's all. Yeah, it's all this algorithms are kind of like limited in this sense.
Yeah. So I would agree. Sample efficiency, in a way, in the current state of the art algorithm, are sort of improved by how well can you reuse existing samples, right?
One question.
Yeah, go ahead.
The Bernoulli algorithm, I don't quite understand. There's only 2 points there. Rather than having 10 or 51 atoms, only 2 atoms.
Yeah.
Is that what?
So Bernoulli is a special case of the categorical distribution, right?
I get that. So it's rather than having multi-class, you have single class.
Beg your pardon?
Rather than being a multi-class prediction, it's basically a binary prediction.
I'm sorry, I couldn't quite hear you.
Instead of a multi-class prediction, it's a binary prediction.
Yes, yeah. So again, that's why they say with n equal to 2, there's a simple alternative, but you could still use this algorithm that works for multi-class. So Bernoulli is just a special case.
Okay.
Yeah. So yeah, overall, I would say this is very interesting. But of course, I see already that there are very limited. There's going to be limitations. In particular, I guess just by seeing it, is that you have to sort of know what's the Vmin and Vmax, and that's not necessarily known in a new domain. And another thing is that the computational time is longer because you have to calculate the number of atoms. And something that now that you mentioned about it is actually makes me a little confusing. So if they choose Vmin to be 10, right, to be 10 or negative 10, how can the algorithm learn the environment where the value should be something like 400?
So the value is for a given state.
Yeah, but if you're at the original states, then assuming you're at the optimal policy, the value of the original states should be the optimal reward that you get, right?
So Here the average score is calculated per game. So you will be summing the values as you go, like as you roll out your transition. But the value for a given state would still be limited by how many points you score at that particular time frame.
I'm not quite understanding what you're trying to say.
So you need to know the reward ranges, right? Range, and then you divide by the numbers of atoms.
That's my understanding, but I think Krishna is trying to say maybe something different, right?
So I mean, so the value of a given state would still be minimum, right? So let's say consider the environment form. So the average score is like maximum average score is 20.
Yes.
So the score is for a trajectory, not for a particular step.
The score are not particular to a particular step, you mean?
Yeah, I mean, so the score is being calculated for the whole trajectory. The value is being maintained for a particular state.
Right. So, the value function is really assuming that given a state, what's the value following the value is defined as a discounted sum of rewards, right? And then the value of the initial states is the discounted rewards given the current state, given the current policy. If your policy is optimal, then your value of the current state really should be the optimal reward. In the case of Asterix, it should be 50,000.
I guess it's maintaining a distribution, but it's more an offset.
I mean, I can understand it if they say, the maximum is just going to be, 10, and then the neural network is always going to sort of build upon that until a point where you reach a state where you say the V max, what you find is the V is actually lower than sort of 10. Then you don't choose that action. Otherwise, you always choose a particular action. Maybe something like that, but I don't know. So I think definitely some limitations on C51, but a very interesting idea. And I wonder, I'm almost certain that people have ported distributional RL into sort of a continuous domain.
Yes, there are distributional equivalent for DDPG.
Yeah, of course, because it's such a straightforward extension. And there we go.
It's like D4PG, right?
Oh, that's what it is? Interesting. How well does it perform, though?
It's quite solid. Close to soft actor critic on some tasks, I saw. Maybe. Not sure.
It almost appears to me that you can combine, this D4PG to TD3, because TD3, the optimizations for TD3 is just something that could be just as well implemented for distribution settings.
I think D4PG already has those crucial TD3 elements.
Okay, yeah, then it makes sense. Now it makes you wonder if the improvement comes from TD3 optimizations or the distributional perspective, right?
Yes.
I don't think so. So TD3 paper is addressing functional approximation. So that's published in 2018, and then D4PG. Oh, they're published in the same conference, so they couldn't have built upon each other, right?
Sometimes it's
actually sorry. This is ICML. This is iClear. But I don't think they're being cited, right? If I just search for this, there's no citation.
Okay. In this case, there isn't indeed.
Yeah.
They compare against CPO and D3PG.
Beg your pardon?
In that D4PG paper, they compare against PPO and against D3PG, but not against TD3.
What is D3PG?
Yeah, that's this one, differentiable deterministic policy gradient. Yeah.
Oh my god. Okay.
It's a zoo.
Yeah, whatever. Okay. Okay. But that's interesting, right? D3PG is submitted in 2019, but this is iClear 2018. Am I missing something here? Anyway, perhaps it's not that important. So there's one more thing that I think maybe we should try to sort of solve or spend a little time on after this monthly development cycle, or maybe it could be part of this monthly development cycle, which is to sort of trying to apply more games into the Atari domains. I don't think Atari domains take that long to run. Maybe you spend 3 or 4 hours on the Atari games, but it's not notorious. It's not that bad, and I think we should do it because there's a lot of algorithm that people have shown that their algorithm. So, for example, PPO, it really should work with Atari as well, but we haven't done too much experiments with PPO working with Atari. So I think it's important that we try to do those things. Just trying to make sure that our implementation is very versatile and work with a variety of different games. And plus, it makes evaluation easier because right now all of the discrete action domains that we can evaluate is sort of Carpal or Lunar Lander, and we sort of run out of fixed experiments that we that have discrete actions. The discrete action domains really comes in from Atari. So, yeah, that's kind of what I have. All I have to say about this paper. Any other questions or comments?
So if you're implementing this for the next week,
Beg your pardon?
so we are implementing this for the next week, right?
Yeah, of course. So, for those of you who haven't tried implementing, what I would suggest is to take a look at some of the algorithms that are already implemented. So, for example, this is C51, so it'll be similar to having a replay buffer. So what you can do is to find something like DQN and just to try to read the source code for it. But in sort of a very high level, you should use the file, just copy this file and then start a new file and save it as C51. And then you start modifying things. In particular, try not to modify the lines that are marked with "try not to modify," because they're really trying to set up the environment correctly, make sure your results are reproducible, and so that when if you have any questions or with the implementation, it will be easy to check on each other's implementation because we have sort of a similar structure using the same replay buffer, using the same seed. So we know exactly what's part of the implementation that went wrong. And you should try to modify the part with respect to algorithm logic. So for example, the Q network is got to change. So instead of being the output shape, it should be the output shape times the number of atoms, right? And that's something like that. And you can use let the number of atoms being part of the arguments. What you would do is you sort of start this and say num atoms equal to, in their paper, I think they use 50. So I'm going to use 50 here. And just add a description, the number of atoms. And then over here, you can just say that the output shape times args num atoms. And then you sort of go from there. And then you try to modify some of the lines with respect to action generation, something related to how you train a neural network. And overall, yeah, that's a recommended way of doing the implementation. Does that make sense?
Yeah.
Okay, perfect. Yeah, so I don't know if you were familiar with the way that you can run the experiments, but to give you sort of a quick recap, usually the experiments are run by using the command line arguments. So it will look like something like this. So for example, you would use something like this, where you use the XVFB to sort of record the videos that are being run, and then you toggle the production mode, which sort of upload the results to weight and biases, and you use a capture video to record the video. So as an example, if you were to run the lines over there, this is what will be outputted in the console. Which is taking quite a long time.
I had a question.
Yeah, go ahead.
Is it at all implemented to load a pre-trained checkpoint and then just do predictions?
Unfortunately not. I don't have that implemented, but that would be something. So before I jump into that, though, I just want to give you a quick introduction of the sort of the console to Krishna, so that when you do the training, all of the results are updated live. You can see the episode rewards, but you have to select the x-axis to be the global step. So that's kind of a niche thing. And you can see the arguments that you run it with, and you can see all of the metrics with respect to your experiments. You can see, in particular, what code resulted in a change. And you can see the videos, right? This is you can see the agent's performance at different time steps. So I think that's really cool and really helps you to understand the performance of your agent, in addition to just the scalar rewards. And to answer your question, Ali, which was what question again?
Yeah, I'm saying that it would be cool to have something where you could load a pre-trained checkpoint and then do predictions.
Yes. That's a very good question. I want to address that a little bit. So I would imagine that shouldn't be something that will be implemented in the core algorithm, because it'll make, maybe it's not that bad, but so first of all, if you were to implement it yourself, it's extremely easy. An example might look something like this. There's only a couple of lines. I want to see if I have a good example on this. Yeah, it would be sort of look something like this, where you're essentially getting the PG state dictionary and just kind of save it, and you can use the weight and biases to save it as well. However, my main reservation with implementing things like this is that overall it'll increase the complexity with the training, and you have to deal with things like, do you want to lull the model that are being trained given a particular reward? given a particular seed, I don't know. There's some design choices to be made, and I sort of defer those design choices because I think if you actually need to do it, it will be easy to implement. But as a core algorithm, it should be as simple as possible.